Hello everyone, welcome to the course of electronic circuit analysis. In this course, in this particular session, let us see the simulation part of common emitter amplifier circuit. When we consider a practical integrated circuit, there could be several millions of components interconnected together. So it will be very difficult to mathematically calculate on a paper. So in this case, we can use the simulation tools for easy analysis. As a startup, let us see the analysis of CE Amplifier Circuit, how to build a CE Amplifier schematic or circuit, which is called a schematic, and see how when we give some input waveform, how the output waveform is appearing. So in particular, we have several simulation tools. Out of those simulation tools, we have SPICE models. SPICE models are the tools which are nothing but simulation program. It is a simulation program with integrated circuit emphasis. So basically, it is developed by Linear Technologies company, hence it is called LTSPICE. Similar kind of versions, similar kind of simulation softwares we have as Multisim, which is developed by NI, and PSpice by Cadence. Likewise, some simulation softwares are available where we can design the circuit and we can analyze the circuit as well. So let us start the work. Let me create a new schematic file, new schematic, which is the circuit. In this circuit, I would like to see the CE amplifier analysis. Let me replace the components first. Component I want to choose here is NPN transistor. So in the search bar, let me type NPN. So that way a particular transistor will be selected, device will be selected, the NPN place. So that we can place it anywhere on the screen. The moment we place, and we are supposed to do the right click, otherwise image will be coming in. So right click, the transistor will be gone, second image will be gone. So we can zoom in or zoom out such that we can place other components as well. So a CE amplifier circuit consists of mainly a transistor and resistors, which are nothing but biasing resistors we have. Resistors R1, R2 at the input side for applying biasing, and we have a collector resistor and emitter, which is a feedback resistor. And of course, we have a load resistor, which is, let me call it as R5, right click. In addition to the resistors, we also have capacitors. So let me place on the capacitor icon, place the capacitors here. So in order to place the capacitor, one bypass capacitor is there. Let me place it just beside the R4 bypass resistor. And the capacitor, coupling capacitor, in order to place it at the input side as an output side, generally we place it in a horizontal direction. So in order to move that vertical component to the horizontal icon, we can press the symbol Control R. Controller can be used. So I pressed once controller, and so that I can place it here on the input side as well as output we observe at the collector. So collector side also I'm connecting the coupling capacitor. So right click, the component will be gone. So once the transistor, resistors, capacitors has been given, we let us apply voltage source. Two kinds of voltage source we have to apply. One is DC voltage source as well as AC voltage source. Let me put voltage source here and tell me, let us keep one voltage source here at the input side, and at the VCC is also one kind of DC source, but VCC is a positive. So this has to be rotated twice in order to get positive. Control R, and place it here. Right click. Not only these voltage sources, we also have ground connections. This negative should be grounded here. So I'm placing a ground here, one ground here I'm taking. One more ground for these resistors and input, all the components we have the ground. So two grounds I have taken. Now, having placed all the components, we will use wire option to interconnect these devices. So the wire option, so it will is a plus icon from where to where, from the, say for example, from the transistor to the capacitor seat. Now, say for example, now the resistors has to be connected through this base. So unfortunately, some students might do the mistake like this. The R1, they have clicked on R1 and they might directly connect to R2 by mistake. It means that this resistor R1, R2 are connected, but it is not connected to the base of the transistor. So if it is base of the transistor is connected, some kind of solid square icon will come here. So if it is not coming, it means that some wrong connection is there. So how do we correct this wrong connection? Means we have an option called delete or backspose. So delete mode. click on the delete mode, and we can remove that particular connection and reconnect it by using the wires. So this is what we can do. So connect the resistor R1 to the base of the transistor such that this node has been come. No new node has to be come. R2 has to be connected to the resistor R1. So likewise, we can click on particular resistor R1. If you want to change the direction, immediately it will not change. We are supposed to click or right click so that the position will be fixed there, and then you can move the cursor from there. Again, wherever you want to go, change the direction means you need to click and change the direction. Likewise, we interconnect all the components, the coupling capacitor, output we observe at the coupling capacitor, and then main output we can observe through the load resistor RL, and the transistor emitter is connected to the feedback resistor, which is nothing but R4 in this case, and input, let me connect this input all grounds. Input positive is applying to the coupling capacitor. The second bypass resistor is grounded, and the coupling capacitor is also bypass capacitor is also grounded here. Bypass capacitor, to reduce the effect of gain reducing emitter resistor, we use the bypass capacitor. So likewise, we interconnect all the components. Of course, this VCC has to be connected. Positive is connected to this circuit. Negative has to be grounded, which is a common point. And this is also the same common point everywhere on the cell. So likewise, once we build a circuit, this is called schematic. So PSpice or SPICE or LTSPICE can understand two kinds of things. One is schematic. The schematic will be converted in terms of lines of code, which is nothing but netlist. Netlist is the lines of code where the simulation software can understand the schematic, which node is connected between, which element is connected between which two nodes. The nodes, the element, its value. That's what the syntax. So here the elements are nothing but here two voltage sources are there, which are represented with V and V. The instance name is V1, V2. Similarly, resistances are R1, R2, R3, R4, R5 resistances. The values are R by default. So capacitors, C by default. So we need to change these values. We need to apply based on the design specifications. We need to fix these values, right? Let me start with by when we right click, DC value can apply. DC value, let me give 15 volts DC value, 15, press OK. 15 will be appearing here. And coming to the AC, instead of direct value, we right click. Instead of DC value, press on the advanced options. We can see pulse, sine, exponential. So let me apply sine waveform of no DC offset and having 50 millivolts peak voltage. 50 millivolts, we can mention like 50 m, small m, 50 millivolts, and the frequency of 1 kilohertz. Generally, 1 kilohertz frequency we take for simulation purpose. So small signal AC analysis, let me take the same AC amplitude in order to analyze AC analysis also. So after giving these four values, press OK. The moment we do that, it is a sinusoidal waveform of zero offset, 50 milli peak volts, and 1 kilohertz is the signal frequency. That's what we get. AC analysis also considering 50 millivolts. Now coming to the resistance values, obviously the resistance R1, the value of R1 resistor should be much greater than the value of R2 biasing resistor. So the resistance R1, right click on that and change it to the 47K. Resistor R2, let me take 4.7K and click on OK. And collector resistor, emitter resistor. Emitter resistor is being gain reducing resistor. Let me take a less value, 220 ohms. And collector resistor, I can take either 2.2K or 3.3K. Let me consider 3.3K. And we observe output across a load resistor. It can be like 1K or 10K. So it depends on the load. So having given the voltage source values, resistors values, let me give the capacitor values. Let me right click on the component. The capacitor value can be like 10 microfarad. Capacitor values in the order of microfarad. So micro is mentioned with the symbol U, 10U. When we give 10U here, that will be taken as 10U. The values of CC has to be changed, right? Right click on the component, not on the instance. If we change the instance name will be changed. That is not what we want. We want the value of the particular instance we need to change. So let me give this 10 microfarad again, coupling capacitor, and bypass capacitor, let me change to 47 micro or something like that. So having uh, design after completing the design of the circuit and giving the values based on the pen and paper work for simple circuit. Now we can carry three kinds of analysis for the CE amplifier circuit. The first one is DC analysis. In the DC analysis, we observe the Q point, which is nothing but VCEQ, comma IC, the coordinate. The second one is transient analysis. In transient analysis, which is nothing but analysis of input output waveforms with respect to time. With respect to time, how the input waveform and output waveform is changing. And the third one is frequency analysis or AC analysis. Like what is the frequency response of this CE amplifier circuit? Means what is the range of frequencies over which gain is constant. That's what bandwidth we are supposed to calculate. We are supposed to calculate highest cutoff frequency, lowest cutoff frequency, and we can measure the bandwidth. These three analyses we are supposed to carry out for this circuit. Now, how do we carry out that? Click on the analysis button, configure analysis. So there are several options here, transient sweeps, AC analysis. Let me first opt the DC operating point, DC operating point. The netlist syntax is .op here. For the netlist syntax, which system can understand .op for DC operating point. Nothing to mention here. Press OK. And this particular icon will be coming. We can place it anywhere on the screen, .op. And we run it. We can see the operating point values. Operating point, not only operating point, what are the voltages, currents in the entire circuit will be appearing here. We are interested in this particular node as well as voltage at this particular node current. So current flowing through the resistor R3. So let me run it and we can see the operating point analysis. See, the operating point for this is like the node, whichever I'm talking about here is, this node is 002. By default, it allows it's as a first node, whichever we connect, it is 001 and then 002, or we can manually change the node value as well. So however, here the VCE is nothing but 7.9 volts is the VCEQ, which is a Q point, which is 7.9 volts. And the current flowing through the resistor R3 is what? Our collector current, right? So current through R3, yeah, I could find it. Collector current through R3 is around 0.0021, which is turns about to be 0.2 milliamps. So depending upon the circuit values and all, we fix it the Q point. So this is the step one. And the step two is we do the transient analysis for this same circuit. How do we do the transient analysis means? Let me click on this AC button again. Click on the transient. For how much time frame I would like to observe the waveform? 10 milliseconds. Say for 10 milliseconds, let me observe. So stop time at 10 milliseconds. Stop time at 10 milliseconds. So let me, when the moment I press it, the transient 10 millisecond, up to 10 millisecond it is coming. When I press play button, another new pane will be opened. So since I have observed the DC Q point analysis, I am getting voltage as well as current here. If I don't want, I can simply click on that and delete this trace. If I don't want this current, I delete this trace. But what I want to observe the input waveform. So I place the pen symbol, whichever is coming at the input. I can see the input waveform. The input waveform is coming blue, which is not clearly visible. So I right click on it and I can change the default color to something like input. I would like to see in the blue color input. So input I have given 50 millivolts peak voltage, positive peak, negative row peak is also minus 50 volts of frequency 1 kilohertz. Frequency 1 kilohertz means the cycle time required to complete one cycle is 1 millisecond, right? Time. So this is what the input waveform I have given. For this particular input waveform, what is the output waveform is coming? That's what we are supposed to observe. So let me observe in some other plot. Let me create another plot window. I right click on this plot. Add plot plane above or below. So let me add below so that input is on top, output is on bottom. Let me click on the schematic again. I will get the pen icon. This let me probe the probe. Let me keep it at the output of the circuit. So the output of the circuit is coming and let me change the color again to red. The output is red color, say for example. So when we see here, when the input is two things we can observe here for CE amplifier circuit. Amplifier has to increase the signal strength. So 50 millivolt signal strength has been increased to 1.8 volts. 1.8 volts has been increased. The signal has been significantly, the signal strength has been amplified. That's fine. And coming to the CE amplifier, one more quality is it produces 180 degrees phase shift. So whenever positive peak is going from 0 to positive, input is going from 0 to positive, the output is going from 0 to negative. CE amplifier produced 180 degrees phase shift. The two things has been clear from this transient analysis. Transient analysis means how the input output waveform is changing with respect to time. That's what transient analysis. The last third thing we are supposed to observe is AC analysis or frequency response of this particular CE amplifier circuit. In the AC analysis, the type of sweep we choose a semi-log. For a semi-log graph sheet we choose a decade, and number of points per decade let us choose 10, and the start frequency from right from the 10 hertz, or say for example right from the 100 hertz, let me observe up to 10 gigahertz, 100 hertz lower cutoff frequency, 10 gigahertz. How this amplifier is amplifying the signal with what gain? Let me observe that through this AC analysis. Press on OK. The moment I do that, the netlist will be coming here. Let me place the netlist over here and run it. Now this is what running. So again, some input output waveforms are coming here. The input waveforms, I don't want to see the input waveform. I can hide it, or I can delete this pane. And one more important point, if we are unable to observe here, like the frequency response here, lower cutoff frequencies, lower frequencies gain is falling, but I am unable to observe gain falling at high frequencies. It may be happening at some other frequency. I want to observe means I can play with the circuit elements, or I can change the transistor also here. The transistor, let me choose a transistor by right clicking, pick a new transistor. So I can choose national semiconductors or Fairchild or any other thing. For my particular application, for my particular design, I would like to choose BC847A, B or C, whichever it is. So press OK. So by changing the components here, the transistor values or resistor values and all, our frequency response curve or input output waveforms will also be changed. Let me see that. Let me run it. See, we have lower cutoff frequency. See, it is coming from 100 hertz. Maybe if I go beyond like 10 hertz or 1 hertz, I may get a lower frequency like this. So let me show that point also. Like right click on this, DC. Right click on this AC analysis. Instead of start frequency 100, I'll put 1 to 10 giga. Let me go. Right, 1 to 10 giga, or I can stop it at 5 giga also based on the response. Let me stop it at 5 giga, 1 to 5 giga, and rerun it. So I'm going to get some kind of curve, like at lower frequencies, the gain falls due to coupling capacitors, which are C2, C3, and at higher frequencies, lower frequencies, gain falls due to coupling capacitors and bypass capacitor, which are external. And at high frequencies, amplifier gain falls due to transistor internal capacitances, high parasitic capacitances, right? Now there are two things we can observe in this particular curve. Again, we have a magnitude curve, which is on the left hand side, the scale, and the phase curve, which is on the right hand side with respect to frequency. I'm not interested in the phase. I know already I have seen in the transient that phase is 180 degrees. So I will right click and don't plot phase. So only magnitude plot I am able to observe. So in the magnitude plot, I would like to mention lower frequency, higher frequency. So how do I mention means that let me right click here and place cursor on active trace. So the moment I do this, the first trace has been come. I can move this cursor here and there. I can see some values here, like the maximum gain. The maximum gain is around 11.8 here. If you observe, maximum gain is around 11.8. 11.8 is maximum gain. So 11.8 dB, decibels. So the gain maximum 1 by root of the maximum value or 3 dB point will give the lower cutoff frequency. So 11.8 minus 3 is like 8.8. So let me drag this component position 1 to 8.8. Yes, I could see 8.85 approximately. So I will stop there. So what is the particular frequency? It is around 100 Hz to 1 kHz, or I can observe here like it is 369 Hz. Not only the lower cutoff frequency, I can also observe the higher cutoff frequency by adding one more active trace. So right click. Again, let me get this second trace here. Let me place like 11 is the maximum. It will not change, right? Maximum 11 minus this 3, it is 8. So around 8, I have fixed this second trace. The first trace, second trace. So first trace gives lower cutoff frequency, which is around 360 Hz. The highest cutoff frequency is around 100 megahertz. That we can see it clearly. So 369 Hz and 83 megahertz. Now the difference between highest cutoff frequency and lower cutoff frequency will give me the bandwidth. The bandwidth of this particular CE amplifier circuit I designed is 83 megahertz. Again, depending upon the circuit components and the transistor, very importantly, transistor specifications, the data sheet we should follow. Based on the data sheet, depending upon the manufacturer transistor specifications, we need to design the circuit, other circuit elements, right? So based on that, we will get the desired input output values, the gain, frequency response we can design. So the SPICE, to conclude the session, like the SPICE is a simulation program with IC emphasis. Particularly in this session, we have taken the example of common emitter amplifier circuit. An amplifier circuit should increase the signal, weak signal strength applied at the input. So we have three things, especially whenever we come to the amplifier: DC analysis. DC analysis for fixing the Q point, we have observed the key point VCE, IC by checking this dot OP. And we have observed the transient analysis, how the input output waveforms are changing, how the small signal has been increased, the signal amplitude has been increased, and also for CE amplifier 180 degrees phase shift, how it has been produced. And the third thing, the frequency response or AC analysis, how the bandwidth has been calculated. We can save these responses or schematic by simply right clicking on it, copy image to clipboard. We can take it to the paint or Word. We can save it, our work. Like this, we can perform simulation of these experiments in this using this LTSPICE. Right? Thank you.